Here we have an equation of a sine function that we are going to graph right now. And we have been reviewing transformations of functions as they apply to parent functions that we learned last year. We've been kind of making sure we're refreshed and sharpened with that. But you're going to see if you're not good at that, it's going to hurt you as you try to do something like this. So it all builds on each other. We also already reviewed the parent function of the sine graph, and we should know what a negative does to the a value. This is a -4 as my a value. We should know what a number greater than 1 does for a number greater than 1, what it does for b. B is not negative. And we're going to talk about how with the trig graphs, we have a way of dealing with the negative b value, so you'll never have to really deal with it very much in the future. We should know what it does when you add a number inside of these parentheses to your x or theta, whatever your input is. And we should know what it does when we add a number to the side. So all of these do different things. So click on the side in your head. Maybe you write it down. Maybe you have it in your notebook. It's up to you, but if you are pretty strong at it, you should know the parent function in your head of y equals sine x. I'm not going to go too far into it. If you need more help with that, I recorded myself going over that last time. But this will be the quadrantal angles from 0 to 2 pi. What's exactly between 0 and 2 pi? Pi. Exactly between 0 and pi? Pi over 2. And then this is 3 pi over 2. This is all happening hopefully in our brain. And then I'm going to go through, and this is 1 and this is -1. And then sine at 0 is 0. Sine is 1, 0. Here it's -1. Sorry, it's overlapping that. And back to 0. And then repeat, 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 repeat forever and ever and ever. So this right here is one cycle. The period is how long it takes to restart one cycle. The period by default is 2 pi. You would divide it by your b value, because the B is in that bonker house and everything's bonkers in there. So that stretch and compression is sort of inverted, has an inverse relationship, and as one get, or reciprocal rather, I shouldn't say inverse, as a reciprocal relationship, which people even talk about reciprocal relationship when you talk about things in science or psychology. So, you know, they work against each other. One gets bigger, the other gets smaller, kind of that way. So you would divide by it. The reciprocal function is even 1 over x, you know? So 1 over b, or 2 pi over b, figures that out. And then I wrote down Q for us, and I just said we find a quarter period, which is 1/4 of the period, and that's just going to tell us what we add. Boom, boom, boom. What's a quarter of 2 pi? That's 2 pi over 4. What does that reduce to? Pi over 2. So if you know where you start and you just add pi over 2, you'll get all the other tick marks. Amplitude, it's going to be the distance from the sinusoidal axis to the max or the min. Now, that should all happen in your head. Mini review. I'm going to draw this. When I draw this, I kind of draw the shape, the picture first, and then the labeling isn't going to be to scale. And that's just like math on the side. And that's what makes the difference of your answer being right or wrong. And then I draw my axes in at the end. So what the heck am I talking about here? I have a negative in front. A negative in front, a, as we reviewed with somewhere over here, the square root function. If a is negative, it's a vertical reflection. That means this is going to reflect and it will have that kind of a shape instead. The 4, if a is greater than 1, right over here, absolute value, I don't care that it's negative, I'm just saying 4 is bigger than 1, it's a vertical stretch. So instead of these little humps going up to 1 and -1 and down to -1, we're going to stretch it by 4. So the highest point, my maximum, will hit 4 units above my midline or sinusoidal, and my minimum will hit 4 units below the sinusoidal axis or my midline. I don't want to say above or below the x-axis because my graph is actually going to move up. How far up? 6 units up, plus k, up k, right? Here, plus on the inside moves it left. How far left? See, left h units when it's a plus h, it's moving left from 0. So it's moving left 5 pi over 7. That's not so bad. That's our starting point. That's going to be this dot. The 3 is the most annoying one. 3 is our b value. If b, the absolute value b is greater than 1, it's actually a horizontal compression. If we go to our period formula, 2 pi over b, the period of this will become 2 pi over 3. Leave it like that. That is, if I have like this little baby sketch, this is not my real graph. This over here is what my shape's going to look like. I have 5 values that I really want to label where they're at. And the distance from here to here is going to equal 2 pi over 3. But I also want to know a quarter of that. Why do I want to know a quarter of that? If I know where I start as an x value, then I just add that amount to get that tick mark, then that one, add it again for that one, and add it again for that one. Instead of trying to like, oh, add your whole period to figure out that last tick mark, whatever. If you stretched or compressed your whole period here, I compressed it by 3. So the length of 2 pi is now 2 pi over 3, literally. It's shorter. Between 0 and 2 pi, I will see 3 full cycles. If I look at the window between 0 and 2 pi, I will see 3 full cycles of this graph. My frequency is increased, it's tripled. But if I stretch or compress this, it's proportional. So each of these little quarter-sized pieces is also going to compress by 3. So all I do to find a quarter is I just find a quarter of the period. So what's 1/4 of 2 pi over 3? Maybe you do, 2 pi over 3 times 4, so that's 2 pi over 12, which is pi over 6. Now, the denominator we use, we'll figure out. Usually we want to like try to think of it with the smallest number. All right, so that means I'm going to add pi over 6 to wherever I start, left 5 pi over 7, that's where I'm starting. I'm going to add pi over 6 4 times. That'll get me that tick mark, that one, and that one. So if you did that all on your own, because we didn't get too heavy into that, if you were able to figure that out, amazing. Give yourself like the best high five ever. So let's see what we're going to do here. I'm going to go ahead and I'm going to draw my midline. And I'm just going to worry about weaving my sine wave around my midline or sinusoidal axis. My sine wave normally goes from a 0 to a max to a 0 to the min to a 0. 0 is another word for x-intercept. I had a vertical reflection, so I'm going to go from a 0, instead of to a max, up 1 unit. I'm going to go to a min, but I'm also not going to go down 1. I'm going to go down 1, 2, 3, 4 units. Put a dot. Bam, right there. I'm down 4 because there was a stretch of 4. Then evenly spaced, okay? I'm not putting the tick marks here because this is not the x-axis. I'm just graphing it around my sinusoidal. I'll deal with it in a second. About evenly spaced, I hit another 0. Because when you reflect, the zeros hold on. That's the little hands of your graph, like a gymnast on those parallel bars, and it's just flipping around, okay? Simone Biles again. So we're here. Normally you would go to a min. I'm gonna go to a max. Why? It flipped over. Instead of going up 1 though, it stretched. It had a stretch of 4. 1, 2, 3, and 4. And then I go back to a 0. Even if I flip it or stretch it, 0 is still 0. I'm back over here. At the very least, your shape should look like this. If your shape doesn't look like this, you're right off the bat on the struggle bus. Okay, we got to get off the struggle bus. Your shape should match the parent function shape. And again, if it doesn't match that shape, usually I know it's like you graphed it on the computer and a calculator and trying to mimic what you see, because obviously this wave is going to go on indefinitely in both directions. And how do you know which piece to draw? That's why looking at it graphed is not that helpful. It's going to be confusing, okay? Now we're here. Next thing I'm going to do, think about my axes. So I took care of the negative and I took care of the 4. Plus 6 is how high up I went. That's 6, 5, 4, 3, 2, 1, 0. What does 0 mean? That is my x-axis. I'm being cheap and drawing it that way. Make my life easier. There it is. On my x-axis, I need the 5 tick marks. 1 under this, 1 under that, 1 here. I'll shift it up a bit, so hopefully it's not going to cut out. Okay, one under this, one under this. Now, again, I didn't draw my y-axis yet. Why not? I don't know if these are all negative, if these are all positive, if there's a little of both. Maybe that's negative, that's positive. So I don't want to draw my y-axis until I know when my tick marks are going to cross over from negative to positive or whatever. Okay, so now what did I just take care of? I really just took care of the +6. This equation of my sinusoidal is y = 6. Next, dealing with the inside. I'm going to start with the 5𝜋/7. That meant left 5𝜋/7. So that means this tick mark is literally negative 5𝜋/7. To get the other 4 tick marks, I need to add. How much do I add? I add a quarter period on. Because if you add a quarter period 4 times, you add the whole period. The period is how long it is from here to here. I don't want to just add the period, try to find midpoints. Midpoints of fractions. We're going to be here all day. So I have to add pi/6. My denominator is 7. That's unfortunate. I need a common denominator, but my common denominator, least common denominator of 6 and 7, I know the word least is in there. It's not 6. The least common denominator of 6 and 7 is 42. So that means for my quarter period, I'm just going to do it over here with my common denom. So this is me like dealing with the common denominator just on the side, okay? My quarter period, instead of pi/6, I'm going to think of it as 7𝜋/42 because I multiplied on top and bottom by 7. This, my starting point, I don't know, whatever you want to call it. My starting point was -5𝜋, or starting tick mark, was -5𝜋/7. I don't know why I wrote that again, but I'm going to multiply it on top and bottom by 6. So I'm going to think of it instead as -30𝜋/42. I multiplied on top and bottom by 6. Same number, same number. If you even wanted, you could change this, or I'm just going to kind of stick it over here. So I know this is also known as, AKA, -30/42. I mentioned when we were solving trig equations, like don't even bother reducing sometimes. It's better to leave that common denominator because you'll be able to see if you are adding correctly and going up by the right amount. And then it helps you check, because if you see the distance from your starting point to your finishing point, and you could see that it is the length of the period, you know you're in good shape. Okay, -30, I'm going to keep adding 7. So -30𝜋/42 plus 7𝜋/42. This tick mark is -23𝜋/42. Add another 7. I got to keep moving. What is this? Another 7 to that. -23 plus 7 is -16. That's a 6. 16𝜋/42. Add another 7. And that -16𝜋/42 plus 7 is -9. -9𝜋/42. Add another 7𝜋/42, and we got -2𝜋/42. That means if I want to go ahead now, and I took care of that, so that's done. If I want to go in now, and that's really taken care of because I used it for all this, and draw my y-axis, I could sketch that in. And again, you don't have to be totally to scale, but that's negative. So my y-axis has to be to the right of that. If you drew it ahead of time, you can't really know for sure that your whole graph is going to fit in quadrant 2, your whole cycle. You know, I know this is not really to scale. Okay. So we could do one of these bad boys, like a little squiggle there to fake it. So this is going to be my x-axis. If you had a theta, it's your theta axis. It's your input. This is my output. If I want to put some tick marks, I know I wrote all over this, but this right here is probably important to label. This is important to label, and this is important to label. I don't need you to give me 700 tick marks. Please don't go crazy. I would label this. That's a 6. I know my amplitude was 4, so I'm going to label that 2, and I'm going to label that 10. So I'll just go over that with a quick highlighter because I made a mess writing on top of everything. Okay, those are my important numbers on my y-axis. These are my important numbers on my x-axis. That is equal to that though, so we're good. I don't care which one you would put. A lot of times I end up putting the one with the common denominator. If you think about how far apart are negative 30 pi over 42 and negative 2 pi over 42, that would be 28 pi over 42 apart. And 28 and 42, they are both divisible by 7 at least. If I divide by 7, I get 4 pi over 6, which is 2 pi over 3. And that is my period. Check. Good to go. And that's how you graph one full cycle of a transformed sine function. Just to wrap it up though, I'm going to write down the domain and range. The domain, my sine function really continues indefinitely in both directions. Whee, like this. So the domain is really negative infinity to infinity. And then the range, visually from the graph, normally your range for sine is from -1 to 1. We stretched it by 4. We flipped it, but that doesn't really affect the fact that the range is still -4 to 4. And then we took everything, we added 6 to it. So the 4 and the 6 are what affect your range. So my range is now from -4 to 4 became from +2 to 10. We use brackets to include it to use our interval notation. And that is the end of that example. If it at least made sense to you, I know that doing it by yourself is still hard, but if it at least made sense to you, if the instruction and explanation on everything is clear, at the very least, put thumbs up on it if you're watching it online later. And if you are not clear on it and you're like, need a different explanation or more explanation, just put a thumbs down for my records and I'll go from there. And if you have a question about this example for the recording and you want me to keep it on the recording, you can ask now. And if you just want me to end the recording, you can let me know. So does anyone have a question on this example? You could just shout it out if you do. Alice, you have one?
Yeah. Would we have to reduce the numbers or no?
I'd leave them. I would leave them, to be honest. If you're sketching it yourself, it makes it just a lot easier. Most of the time, the numbers aren't that big. I was just trying to make a point in this example where you might have to find a common denominator. I have this like weird habit where like somehow in my brain, I always give these like nice numbers and it automatically gives you a common denominator. So I just tried to intentionally throw a 7 on there so that I knew it wouldn't be common because 7's prime, blah, blah, blah. So I intentionally gave you one that was annoying, but I would leave all the denominators the same. It makes it much easier for you to see that they're evenly spaced apart, you know? So don't worry about reducing them. Any other question about this particular example, or we're good for at least good on this example? All right, so I'm gonna end that recording.